Welcome to the lecture on electrical circuit analysis. So, today lecture is on duality and dual networks. Let us discuss what is meant by duality, what is the concept of duality and dual networks. So, the learning objectives of this today lecture is, the first one is to understand the duality, what is the concept of duality, and the next one is to draw the dual networks and to solve how to draw the dual networks and to solve the problems on dual networks. So, concept of duality and dual networks. So, what is meant by dual networks? So, dual networks are one in which currents and voltages are interchangeable. That means, current source is changed to voltage source is changed into the current source. If that is possible, then the two networks are said to be duals of with each other. When two networks are dual of each other, if one has the mesh equations numerically identical to the node equations. See, if you take one network, what are the mesh equations are there? See, two networks are there, network A and network B. In the network A, the mesh equations is same as the node equations in the network B. Then this network A and network B are dual networks. So, what are the rules to follow for evaluating these dual networks? See here, the number of first one is the number of meshes in a network is equal to the number of nodes in its dual networks. So, how many meshes are there in the given network? So, it is a dual network consisting of that many number of node equations. The second one is the impedance of a branch common to two meshes must be equal to admittance between the two nodes in the dual networks. So, impedance in this given network must be equal to the admittance in the dual network. Impedance between the two meshes, admittance between the two nodes. So, voltage source common to both loops must be replaced by a current source between the two nodes. If current source between the two nodes must be replaced by voltage source in the two meshes, vice versa. Okay. Admittance between the two nodes replaced by impedance between the two meshes. Node equations must be replaced by mesh equations. Now, short circuit in this given network can be replaced by open circuit in its dual networks. Open circuit in the given network can be replaced by short circuit in its dual network. That is, open switch is replaced by closed switch and vice versa. Closed switch is replaced by open switch, like that. So, what is the pairs, the dual pairs? Now, see, if it is a voltage source replaced by current source, if it is a voltage in any element is replaced by current in any element, in that element. Short circuit, okay, short circuit replaced by, series circuit, it is not short circuit, series circuit replaced by parallel circuit. Thevenin equivalent circuit replaced by Norton equivalent circuit. I told you when I discussed the Thevenin's and Norton's theorems. So, Thevenin's theorem and Norton's theorems are duals of with each other. That means, Thevenin network can be converted to the Norton's network and Norton's network can be converted to the Thevenin's network. So, mesh equations are converted to the node equations. So, node equations can be converted to the mesh equations. So, KVL equations, Kirchhoff voltage equations can be equal to the Kirchhoff current law in its dual network. Voltage source converted into the current source converted into the voltage source, vice versa. Now, series connection can be replaced here parallel connection. Parallel connection is there in the one network, then there must be series connection in its dual network. Resistance is replaced by conductance G and conductance G is replaced by resistance, both vice versa. Inductance L is replaced by capacitance C. So, if capacitance C is replaced by inductance L, both are so interchangeable. Impedance replaced by admittance. So, admittance also replaced to admittance Y can be replaced by impedance. So, this is the concept of the dual networks, duality and dual network. That means, any network can be converted into its dual network. Okay. So, this source transformation, we know this Thevenin circuit. What is the source transformation? So, any network, any source, any network which consisting of a source, let us say voltage to current source transformation. That means, if the network consisting of voltage source in series with resistance, that is what practical voltage source, can be converted into its equivalent current source, which consisting of current source in parallel with the same resistance, where that value of current source I is equal to V by R. See, if there is a circuit, see from the first circuit consisting of VOC and resistance R1 across the set terminals AB. So, this circuit can be converted into this circuit. Okay, this consisting of current source in parallel with the resistance. So, what is the value of this ISC? This ISC is nothing but this voltage, okay, this voltage by this resistance R1. So, V by R is the value of this ISC, where this R1 is same. So, voltage source in series with the resistance can be converted into the current source in parallel with the same resistance across the same terminals AB. So, this is called source transformation. And also this current source in parallel with the resistance R1 across the terminals AB can be converted into the voltage source in series with the resistance, vice versa, across the same terminals AB, where this voltage source VOC is equal to this current I into R1, the value. Therefore, source transfer voltage source to current source and current source to voltage source transformation networks are duals of with each other. Now, Thevenin circuit and Norton circuits are duals of with each other. So, see here, so circuit A and circuit B, original circuit. Okay, so we want to find out the Thevenin equivalent circuit across the terminals A and B. Okay, Thevenin equivalent circuit across A and B. So, we have converted this network into this. So, voltage source, that is V Thevenins, open circuit voltage in series with the resistance, that is R Thevenins. Circuit B is remains same. Now, this is the Thevenin equivalent circuit for the given original network. Now, this network, for this network we can draw the its dual network. What is a dual network? So, voltage source replaced by current source, series resistance replaced by parallel resistance across the same terminals A and B. So, remaining the original circuit, the circuit B remains constant. Now, instead of that, you please first find out the Norton equivalent circuit for this original circuit. Okay, first find out the Norton equivalent circuit. How to find Norton equivalent circuit? Find out the Norton's current, that is short circuit current, and find the Norton equivalent resistance, which is equal to Thevenin equivalent resistance. You know how to find the Norton equivalent resistance, that is Thevenin equivalent resistance. Okay, once you find the Norton equivalent circuit, that is Norton equivalent circuit consisting of current source in parallel with the resistance, that is R Nortons, the current is I Nortons, short circuit current. So, this Norton equivalent circuit can be, so we can draw the dual network for this Norton equivalent circuit, that is our Thevenin equivalent circuit. So, this current source can be converted into the voltage source that is VOC, which is equal to the ISC into R1, already there ISC into R1, and the parallel resistance can be replaced in a series resistance. So, that is what we have seen here. Okay. So, this is the concept of the duality. That means, for any network or circuit given, so which we can draw the given network or which we can draw the dual network. Okay. So, let us take this example. Find the Thevenin equivalent circuit at the terminals A and B. So, this is the circuit first. So, this is the load RL across these terminals A and B. So, we have to find the Thevenin equivalent circuit. So, to find the Thevenin equivalent circuit, okay, so this for this network, for this circuit, this is the Thevenin equivalent circuit, which consisting of voltage source 30 volts in series with the resistance, that is here V Thevenins and R Thevenins is 4 ohms, we got it, and V Thevenins is 30 volts. Again across the same terminals A and B, okay, across the same terminals A and B, so same load resistance. Now, how we will obtain this 30 volts and 4 ohms? Let us solve this circuit. Okay. So, first step is we have to solve the Thevenin's equivalent voltage, Thevenin's voltage, V Thevenin's. How to solve this V Thevenin? This is the open circuit voltage across the terminals A and B. Okay. Now, you disconnect this element RL, you disconnect the element, now make it open circuit across the terminals A and B, take your V Thevenin's plus and minus. Now, you apply the mesh analysis technique to solve this Thevenin's voltage. So, here see here first minus 32 voltage source is there. So, minus 32 equation applying the Kirchhoff voltage law in the first mesh. So, minus 32 plus 4 into I1 plus 12 into I1 minus I2 is equal to 0. Algebraic sum of the voltages around any closed path is equal to the 0, that is Kirchhoff voltage law. So, application step by step application of KVL is nothing but mesh analysis. So, equal to 0. But what is I2? See here in the second mesh, I2 is directly given because here current source is there, 2 ampere current source. So, 2 ampere is going from bottom to top, that is anti-clockwise direction, but I2 we have labeled as clockwise direction. Therefore, I2 is equal to minus 2 amperes. I2 is equal to minus 2 amperes. So, if substitute this minus 2, I2 is equal to minus 2 amperes in this equation 1, then you will get the I1 and I2. So, what is I1? 0.5 amperes. Once you get the 0.5 amperes, then what is the voltage across the, what is V Thevenin's? So, V Thevenin is nothing but see here, this current source, 2 ampere current source and this 12 ohm resistor are in parallel. Therefore, whatever the voltage will get drop across this 12 ohm resistor, so same voltage will get appear across this current source. But what is the voltage drop in the resistor, 1 ohm resistor? It is 0 because it is open circuit, the current is 0 in the 1 ohm resistor, therefore voltage drop is also 0 in the 1 ohm resistor. Therefore, what is the voltage there in the 12 ohm resistor? Same voltage will get appear across this 2 ampere current source. So, that voltage we are calling as a Thevenin's voltage, V Thevenin's. So, between these two nodes the voltage will exist, voltage will exist. So, therefore, V Thevenin, now tell me what is the voltage across this 12 ohm resistor? So, this element is connected between the two meshes. So, it is a mutual element. The current I1 is entering, see the current I1 is entering and the current I2 is leaving. Therefore, the voltage across this 12 ohm resistor is equal to V Thevenin is equal to 12 into I1 minus I2, 12 into I1 minus I2. That is equal to 12 into I1 we got 0.5 plus I2 we got 2, that is a minus into minus plus 2, that is 30 volts. That is 30 volts. So, once you get 30 volts, okay. Now, how to find out the Thevenin resistance? So, this is a way. So, to find out Thevenin resistance, so first we have to make it voltage source short circuit, okay, current source open circuit, current source open circuit. So, see this network, see 32 volt short circuit, that is only 4 ohm resistor is there, current source open circuited. Now, we have to find out the R Thevenin's seen from these terminals A and B. Now, how it is connected? So, 4 ohm resistor and 8 ohm resistor, this 12 ohm resistor connected in parallel. So, this combination will be connected in series with this 1 ohm resistor. When you are calculating the Thevenin resistance from the right side, we should go from the left side. Okay. So, therefore, R Thevenin see here. So, R Thevenin is equal to 4 ohm is in parallel with 12 ohm plus 1. So, R1 into R2 by R1 plus R2. So, 4 into 12 by 4 plus 12, 16 plus 1. Then you will get 4 ohms. If you solve it, you will get the 4 ohm resistance. Okay. So, 4 ohms. So, this entire network can be replaced by its equivalent Thevenin equivalent circuit. So, that is the V Thevenin, that is 30 volts we got here, okay, 30 volts, and R Thevenin is 4 ohms. So, R Thevenin is 4 ohms, 30 volts and 4 ohms across the same terminals A and B, and again connect the disconnected element RL. Now, this network can be converted into its equivalent dual networks. This Thevenin network can be converted into its equivalent dual networks. How? So, that means this network consisting of voltage source in series with the resistance. Now, we have to draw its dual network, that is that network should consisting of current source in parallel with the same resistance. Now, what is the value of that current? See here, that is what we have discussed here. See, this is the Norton equivalent circuit. This current source, this RL. The circuit B is what? The circuit B is here RL. See, this RL is so this RL is now our here circuit B. What is this current of this I Nortons? That is ISC, short circuit current. Is nothing but, so 30 by 4. I is equal to V by R, 30 by 4 amperes. Okay, so this is 30 by 4 ampere, this ISC, and this R1 is nothing but how much? Same, R Nortons is equal to R Thevenin, that is 4 ohms. Okay, 4 ohms. Again, circuit B is RL. So this is the dual network. How to draw the dual network? So Thevenin resistance, Thevenin circuit, its dual network is Norton circuit. Norton circuit dual network is Thevenin circuit. Okay, so this is what the concept of duality and dual networks. Okay. Thank you for listening the lecture. We will join in the next lecture.